We are highly privileged to host the Faculty Development Program on Recent Research Advanced in Mathematics. Let us start the session with the God of Blessings and Small Prayer. I would like to call a Sister Rexeline to start a session with a prayer.
An administrator with patience and an open mind before they enter the door. Keep flowing through our minds as we face challenging questions and decide how to manage current situations. Show us new ideas, lead our hands as we write, and may we all keep a friendly tone. Be with us, guide us, and direct our words. Please make sure our final decisions are put in place with the best interest of the students in mind. I pray this in Jesus' loving name. Amen.
Thank you, Sister. Thank you for your blessings. Now, I humbly request Mrs. K. Sujata, Head Department of Mathematics, to give the welcome speech.
A warm greetings to one and all present here. From the Department of Mathematics, St. Joseph College, Chennai. It gives an immense pleasure to welcome you all for the 6 days International Faculty Development Program, Recent Research Advances in Mathematics. This program is organized by Department of Mathematics, St. Joseph College, Arts and Science, Chennai, in collaboration with DMA St. Eugene University, Zambia. Of God, the Almighty, and Founder Father, Reverend Father Dr. J.E. Arulraj, the motivation of our sister, Administrator Reverend Sister A. Malarjyoti, and the guidance of our Principal, Dr. R. Ruben, it's my great pleasure to welcome our eminent resource person, Dr. S. M. Mallikarjunaya, Professor of Mathematics and Statistics, Texas A&M University, Corpus Christi, USA, by the topic Fluid Mechanics. A special mention to Dr. R. Kavita, Vice Chancellor, DMI St. Eugene University, Zambia, Dr. S. Herman, Director of Education, DMA Group of Educational Institution, Central Africa, and also Dr. V. Govindan, Research Coordinator, DMI St. Eugene University, Zambia, for the support in conducting this FDP. Also, I welcome our dignified faculty members of our college and our department and other colleges, universities, and across the country. The aim of the FDP is to create the awareness on latest research thrust areas in mathematics among the faculty members. Once again, I welcome you all to the 5th day of the Faculty Development Program. Thank you all.
Thank you, ma'am. Thank you so much. Now, I would like to call upon Dr. V. Govindan, Research Coordinator, DMI, St. Eugene University, Zambia, to introduce a resource person of today's session.
Madam, are you audible?
Yes, sir.
Madam,
you are audible. Yes,
okay,
sir.
okay. Thank you.
Okay, sir. Welcome you, sir.
Good afternoon to all, and good morning, Professor. I am very happy to introduce our chief guest, Professor S.M. Mallikarjunaya, Assistant Professor of Mathematics, Texas A&M University, Corpus Christi, USA. He awarded MS degree of Mathematics 2007 at the University of Rio Grande Valley, Edinburgh, TX, USA. He awarded Doctor of Philosophy in Mathematics in the year of 2015 at Texas A&M University College Section TX, USA. He awarded postdoctoral fellowship in the year of 2018. He worked as a lecturer, Department of Mathematics, RJIT, Dr. 4. Now work as a assistant professor, Department of Mathematics and Statistics, Texas A&M University, Corpus Christi, Texas, USA. He has organized 15 webinars in national and international levels. He was organized 15 workshops in national and international levels. He was completed 8 funded projects. He was guided 15 PhD scholars and is guiding 8 PhD scholars. He was received research support from College of Science in Engineering, that is 1,44,000 USD. Also, he was received a grant project titled Machine Learning Methods for Geophysical Data. He was received a grant project titled Deterministic Mathematical Model for COVID Data and etc. He published 40 articles in Elsevier and Springer in reputed journals. Now, Professor Dr. S.M. Mallikarjunaya, now your session, sir.
Thank you so much for all the nice words. Thank you so much for this invitation. Thank you to my friend, Dr. Govindan. Thank you for inviting me to attend this. It is so nice to meet you all. I'm going to start my talk. Let me share my slides. Okay, I hope you can see this, right?
Yes, sir. Slide is visible.
Okay, thank you so
Yeah, visible,
much.
sir. Visible.
Thank you so much. So today I'm going to talk about an efficient numerical method for a nonlinear fluid flow model. And so this research was done with my former postdoc, Dr. Yoon. He is currently in Kigam, Korean Institute of Geoscience and Mineral Resources, and Dr. Palaniappan, he is a senior professor in our department. And the funding for this research is done through a grant from our university. And I also acknowledge the computations, all of these computations done on a high performance computing cluster supercomputer in our university. So, I mean, the reason to start this project, I'm going to tell that in the next slide. But we all know flows are beautiful, right? But they're difficult to compute. The reason because of the complexity of the physical systems involved and the assumptions need to be made, and then efficiency of the numerical method and so on and so forth. When you trace back towards the real model, you see that we have lost many things in our mathematical assumptions and also numerical methods. So when I was telling you, the reason to start this project is an interesting topic called hydraulic fracturing that is done in the oil industry. The hydraulic fracturing is an oil and gas development process that is typically involves injecting water, sand, and other important materials, chemicals, under high pressure into a bedrock formation via the well. So the blue line here is the well, and then the water and other things are injected into this well with high pressure, and this is to create new fractures in the deep underground to extract the oil or to connect the existing fractures. Okay, and through the network of fractures, one can extract the oil and then it is going under process before it is, we see that in our petrol pumps or gas stations. Okay, so the reason, because the reason to start this project, because this problem was posed to us from someone from in the oil industry, and uh, we apparently saw sorry, we apparently saw some challenges involved. There are already existing models that can describe this procedure, and also there are existing models that can simulate this procedure. So, but then some of them, they uses a very fundamental assumption that is clearly wrong. But when you go back and trace back to the real situation, you see that the results from either mathematical analysis and numerical simulations were not able to match the results people see in the real world. So we started this project, and before we put into, because there are a lot of physics involved here, so before we put all the physics into model or into the partial differential equation system that can describe this model, we thought that we should divide this whole project into several pieces and then handle piece by piece. So that was the whole idea, and this is the main motivation for this project. And also we also need to notice that there is a strong coupling between the fluid that flows into the well and the fracture that created by the fluid flow due to the high pressure gradient. So it is not easy to handle this type of situations with the partial differential equation system. So then we thought, let us handle fluid flow separately and then solid separately, and then we'll try to couple them and then see what's going on. So what I'm going to present today is only the fluid flow model and also the treatment. How do you treat that fluid flow model using a numerical technique? And you will see that that itself is a great challenge, and I am sure we all will appreciate at the end of my talk the beauty of mathematics that can define the situation correctly. So the plan for today is as follows. So first, I'm going to briefly outline um, the numerical treatment that we have come up with to discretize Darcy-Brinkman-Forchheimer model, and then I'm going to describe the stabilization that we did for the inf-soup type of discretization, a type of finite element method that is usually done for the Navier-Stokes equation. And then our technique is simple, but it is very, very effective in handling the numerical oscillations. So this technique is typically we can use in any fluid flow model, but what we see is we have to see whether this is needed, whether we see any numerical oscillations, and how do we control that. There are other techniques that can control numerical oscillations, but ours is a very simple addition of an extra term into the weak formulation. Okay. And then we exploit that extra term that added to develop iterative linear solvers and using efficient preconditioners. And then finally, I'm going to show you some numerical experiments that illustrating our implementation, and then also show that our approach leads to an effective solver for the solution of nonlinear partial differential equation system. And this code especially was developed only to handle the fluid flow model, but we can enhance this code by adding other interesting physical situation or multi-physics situation. Okay, so the mathematical model comes from the nonlinear fluid flow model, which was developed by Joseph and others in the paper in 1982. So they want to describe the fluid flow in the fully saturated porous medium with considering the inertial effects and incompressibility constraint. Okay, so the partial differential equation leads to these two equations that I have presented in the slides, where u, the boldface u, is the velocity. Today, I'm going to restrict myself to 2D problem, so that's why it is in R2, and the pressure is a scalar function. And notice that in the usual fluid mechanics literature, they usually eliminate the pressure and then work on or work with only the velocity system. So we did not want to do that. So we want to keep pressure as a primary variable, and that poses a separate challenge in devising an efficient numerical method. K, phi are the physical variables, permeability, porosity of the medium, mu is the dynamic viscosity of the fluid, and rho is the fluid density, and beta here in the last term right hand side of the first equation is the what is known as Forsheimer coefficient. One can play with this one between Darcy-Brinkman and this full nonlinear. That's why we added that. And F tilde represents an external force, where one can add anything, any external force into this term F tilde. And then omega we consider, so this is defined in a smooth bounded non-convex domain, omega. Okay, so this is the situation right now. So we have to develop numerical method for this system of nonlinear partial differential equations. So we consider a stationary problem. One can add a time derivative and steady and unsteady. I mean, steady and unsteady problem. Our code can handle that also, but for today's talk, I just ignored that term. Okay, so we have to come up with a system that is dimensionless. That means all field variables have to be dimensionless. So that requires us to introduce some dimensionless quantities. So x star, u star, p star are the dimensionless quantities, and they have been dimensionalized with some length and velocities. And then so the dimensionless equations are these two equations now, and you notice that we still have a structure of nonlinearity on the left hand side as well as the right hand side, and then the dimensionless procedure, the non-dimensionless procedure introduced what are known as Reynolds number RE and the Darcy number DA, and some coefficient, dimensionless coefficient CF. So a whole of the problem, the entire problem can be studied as a function of the Reynolds number and the Darcy's number. And if you notice the fluid, especially the finite element literature for the fluid flow problem should be devised for the values of Reynolds number ranging from close to 0 all the way up to like 10,000 or 15,000, something like that. But there is a region where the flow becomes laminar to turbulence, and one has to make sure that the method can takes care of the large Reynolds number value as well as the very small Darcy number value. Okay, so that poses an extra challenge, but again, we can test that with the existing results from the literature before we present the conclusion about our numerical method. Okay, so I have to introduce some notations. Here, my omega is a non-convex bounded polygonal domain with a boundary, with a smooth boundary. And then X be a non-linear space, which has an, LP is a space of Lebesgue integrable functions, which is defined, L2 is defined like that in the first equation in this slide. And that is a classical space of square integrable functions. We have an inner product and corresponding norm. And we define the LP norm by the last equation in this slide. And then we also need to define some classical note. We also need to borrow, because this is not our definition. This is just borrowing from any analysis textbook. So we borrow some classical notations of Hilbert space. So here, x naught. So notice that I have made x naught as bold because we need to approximate two different field variables, the velocity, which is a vector with two components because our focus is on 2D problem, and the pressure, which is a scalar valued function. So we needed h10 to approximate the continuous velocity variable, and we needed L20 to approximate scalar valued pressure variable. And notice that the 0 in H1 and 0 in L2 denotes two separate things. One is 0 here is the trace of that variable on the boundary is 0, but the 0 on the L2, the average is 0 in the entire domain. Okay, I don't want to confuse you, but those are the notations. And then let's denote X as a classical H1 and Q as classical L2. And the H1 norm we needed for our analysis is this, which is given in the last equation in this slide. And then because of the nonlinearity, the problem poses the first challenge that before we derive or we develop or we synthesize any numerical method, so we have to see whether it can handle nonlinearity or not. So basically, everybody does is linearization using Newton's method, and we are not different from all other people. We also did the same linearization using Newton's method. So we take everybody into one like a matrix that has one column with u and p defined. U has two components and p is just one scalar function. And then we seek an approximation to xn where we develop sequence of approximations to our both field variables, and xn plus 1, which is, you can take it as n plus 1 as the Newton update. So xn plus 1 is the old Newton value xn plus some alpha. Alpha is where alpha is that can help us in the convergence, and or we can call it as a step length times the delta xn, where delta xn is the unknown. Okay, so at every Newton step, you are going to compute delta xn and multiply that by some step length and add it to the previous Newton's value. That is going to give you the current value. And then, so there are two things here. One is, how do you choose alpha? The other thing is, where do we stop this iteration? Okay, so we will answer them separately. And where this delta xn is given by the last but one equation, this equation, and the gradient term is the Jacobian. And so the method really is the last line in this slide. Okay, so that's the Newton method. It's just like the in the textbook, undergraduate numerical methods textbook. But the problem here is we have a vector valued problem. Okay, so the calculations are clumsy, but I want to show all those, but I want to show you the final step. So that's the Jacobian term we got. And notice that we have linearized, we have decoupled convective term, which is the first two terms, and we also decoupled the nonlinearity that was present in the right hand side of our PDE model. So that is being decoupled. Now what we are seeing here is a linear problem. So perfectly linear problem. And we can go back and borrow the techniques from classical analysis to come up with the proofs on existence of solutions at the continuous level as well as at the discrete level. Okay. Now let's propose some variation formulation. So I'm going to split the entire thing into small pieces because these can help us in evaluating the convergence of our method and also the stability of our method. So I'm going to define M. M is the term that with the 1 over Reynolds number. So what I'm going to do is for this system, the linear system, which I'm showing in this slide, I'm going to multiply by what are known as test functions from classical Hilbert space to both of the equations. But we needed two types of test functions, one for to approximate the velocity variables. One for the term with velocity variables and one for the term with the pressure variable. And notice that the pressure has a derivative here. So that means we have to think about when we derive a variation formulation, we will do integration by parts. So the pressure loses its gradient, thereby it's bring down from H1 to L2. Okay, so as I was saying before, I'm going to split my entire weak formulation into smaller pieces. So M here is the 1 over Reynolds number term. C here is the 1 over Reynolds number times Darcy term. And B is that pressure block, or you can call it as the block comes out of continuity equation, which is the second equation here. Okay, second equation here. So you multiply by a scalar test functions here. Why scalar? Because of the del dot reduces the variables from vector to scalar. So that let's keep it in B, and then N that contains the nonlinear part of convective part from the velocity. S contains the nonlinear part from the Forsheimer term. So after splitting all this, we assemble everybody into one big equation and call it as A tilde. And notice that here UN, wherever you see UN, that is already known. Okay. So you are computing delta UN. Okay. So UN is like a previous approximation and delta UN is the current unknown. And then once we compute that through some process, we compute the current update and we'll go to the next Newton level. Okay, so this is already posing a challenge here. That is, we have to come up with a proper stable numerical discretization. And we also have to come up with whether whatever we are approximating with the convective term and the diffusion term and nonlinearity from the Forsheimer model, are we approximating it properly? Okay, so that is what we have to consider. Okay, so this is the continuous weak formulation here I'm proposing. I'm proposing like a problem. So find UN plus 1 in X, where remember X is H1, but it is a vector valued H1. And Pn plus 1 with Q0. Q0 is the L2 with the mean 0. And then U at the boundary is some known function G. And notice that we can also impose the normal gradient equal to some function. Okay, so our code can handle that. And then the entire weak formulation is being written as a block of velocity A tilde and a block of pressure B and the right hand side known terms. So Fn handles all the external force term like magnetic or all other force terms, gravitation, those terms, external forces. And the B here, the second equation B comes from the continuity term, continuity equation. Okay, now this is the weak formulation at the continuous level. So one can go back and look at the existence of solution for this system. And because we have linearized, it's not that difficult. we can borrow some standard theorems and prove an existence of solution to this system. Okay, and then now before we talk about stability, we have to consider the in soup condition or Babuska-Bretzi condition before we come up with some continuous test function spaces to approximate both our field variables. Okay, what is this condition? This condition says that there is an existence of constancy where the supremum of this term is larger than that constant term, that constancy. Okay, now this is guaranteed. The existence of this constancy is guaranteed due to the non-convexity of the domain and also the linearity of the problem. Okay, and that is enough for us to prove the existence of solution and uniqueness of solution to this system that we are proposing. Okay, so that's the continuous problem. So but then we cannot simply solve the continuous problem. That is because of the large dimensionality involved in the continuous case. So we have to come up with a finite element discretization. So again, one can do finite difference or one can devise a finite volume based on the situation. But we are interested in finite element. That is because later on in the project, although I am not presenting that today, later on in the project, we have to couple the solid part also. The PDE comes from the solid equation, as from modeling the behavior of the solid. Okay, so but then for at least for the fluid flow problems, again, we were using finite element discretization. Here I'm going to divide omega into smaller pieces of the subdomains, and for our convenience, we are introducing quadrilateral elements. Okay, again, one can do triangular elements also, but our code is written to handle only quadrilateral elements. Okay, so the union, the closure is also taken care, and we don't have intersection between any two elements. If they intersect at a single point, or they intersect along an edge. Okay. Okay, so there are some terminologies from finite element side, and we took care of all those. And for today's work, I am going to define a finite element space called QK, where it is, it is a set with continuous functions. At each cell, it's a function of, it belongs to the space QK, where Qk is tensor product of polynomials up to order k on a reference cell k cap. Okay, so k cap is a reference cell. That means you always do your calculation in the reference cell, map it back to the original domain. Okay. So that was our finite element discretization, and we define the finite dimensional subspaces xh and qh. Okay, and then we also have to take care of discrete inf sub condition. The inf sub condition that I have defined here for the continuous case, we also have to take care of this one at the discrete level. So in order to take care of this one at the discrete level, the way it is done in the finite element literature is you approximate the velocity variable by the quadratic polynomials and approximate the pressure variable by a linear polynomials. That way, this condition is being taken care. One can verify this one if you take the equal order approximations, means you take linear for velocity, linear for pressure, this condition will be violated. Or you take the higher order polynomials, this condition will be violated. Okay, so at the discrete level also, we have to take care of that. Okay, and then, so the discrete problem reads this one. Now, I'm introducing the subscripts h that denotes that I'm at the discrete level. So I am fine. my problem is to find UHn plus 1, which is in XH, and PHn plus 1, which is in QH. By finding delta UHn and PHn at the each Newton iteration level. So because this is a Newton's method, as we all know, we are all teachers, we know that the Newton's method works best only if you supply a good initial condition or good starting guess. So the starting value or starting guess for this is, we go back to the nonlinear problem. You just take the nonlinear problem and solve it using your any known method. Means you drop this nonlinearity convective term u dot del u term, and you drop the nonlinearity and coming from the Forchheimer term, that is nar mu times u. Okay, so that will give you a linear problem. You can solve that. There are hundreds of thousands of methods available, and you can solve that, and you can use that as your initial case. So that means technically in the first iteration, or you are solving actually the linear problem, and then you supply that as an initial guess. You are not too far from the exact solution, and then you start your Newton iteration. So this is what I'm showing here is a Newton iteration. So at every step you find delta un, and then you also find what is known as step length. What is step length? So step length is calculated by the classical conditions, by knowing the residual or the entire norm, and in which, I mean, whatever the direction where the norm is small, and we choose that particular alpha, and then we go to the next one and check whether the alpha we found before was correct or not. Okay, so that's the problem at the discrete level. Now, as I said before, we also have to take care of the in-sup condition at the discrete level. So, I mean, these are like pH and VH. Okay, there is a typo here. So these are pH and VH. What are those? Those are the discrete field variables. And again, there is a proof of this one. I'm not showing that today. It's boring. So that the existence of constant is guaranteed due to the finite dimensional nature of the problem, and also the non-convexity of the domain. Okay, so oops, yeah, I was looking at the wrong slide. Okay, so we have now, what we have is the discrete problem, and then we as I was saying before, if you solve this problem without, like, if you solve this problem without doing anything to this, you will see that you will not have convergence. Okay, and even though whatever the good initial guess you supply, you will still see some numerical oscillations. And then you also you also will see that when you either find some kind of an energy norm, or some kind of a norm for this problem, you will see that you are not going to conserve anything. Okay, so that means there is somewhere that we need to fix this problem. The idea is to add a stability term. The type of stability term that we added is called the grad div stabilization, or augmented Lagrangian stabilization, where you always have parameters. This is like a mathematical calculation type of problem, where you have that some parameter gamma, and then you take it 0 and see whether you converge to some values or not. And for this problem, because of the nonlinearity, you will see that there is no convergence, and then you make this gamma non-zero. Okay, so that is the kind of stabilization we used. The proofs are available to show that with this stabilization, there is an existence of solution. Okay, and then so we have to then decide about what kind of solver we have to devise, and whether we are conserving something or not, right? So again, for the simplicity sake, I'm going to define the matrix entries. So this will be a block matrix entries on the nature of Reynolds numbers and Darcy number. So the first term with 1 over Reynolds number term, I'm going to call it as Mij, and here I'm approximating each of the field variables, the velocities and the pressure, by some test functions. The velocities are approximated by quadratic polynomials, and the pressure is approximated by linear polynomials. So I have 1 over Reynolds number term. I'm going to call it as Mij. These are the entries to that block matrix, and Cij is with 1 over Reynolds number times Darcy number. And convective terms, I'm going to call it as Nij. And terms from Forchheimer term on the right hand side of the PDE, I'm going to call it as Sij. And Bij are the entries from the pressure block. This is the discretization of continuity equation. And Lij are the values obtained, are the matrix entries obtained from the new term, that is augmented Lagrangian term. Okay. Now with these entries, one can come up with the stability argument. Okay. If you go back and look at the weak formulation, so I have clearly separated out what are the contributions from the velocity block A tilde, okay, which is eventually become A by the addition of new stabilization term, and then the pressure term B, and then all the known external forces will be on the right side. Okay. Okay, so those are the block matrix entries. And then if you look at the matrix, nature of the matrix, or type of matrix that we just obtained from our discretization, here we have the first block. If you take this as a 2 cross 2, the 0 cross 0 is the first block. First block contains all terms from velocity, and second block contains the pressure, all terms from pressure term. Okay, so G contains all the right hand side and known terms. Okay, so again, we want to solve this problem as we increase the matrix size. Okay, we want to solve this problem like the matrix size of probably like 10 lakh cross 10 lakh. Okay, which is very time consuming, and then which is also going to exceed the memory or things like that if we just run on our laptops. So we need to do two things. One, we have to come up with a better preconditioner. Number two, we have to come up with a better parallel solvers where you can run the code on supercomputer. Okay, so the way we did was we came up with a preconditioner, which I've denoted here, P inverse, where P inverse Y is X. Okay, so technically you are solving this equation A tilde P inverse Y equal to G for Y. And by knowing Y, you can go back and compute by inversing the by multiplying that vector Y by inverse of the preconditioner. Okay. Now, there are small assumptions made. I'm going to tell them here, and there is a scope for future research here. Okay. Okay. So, where the preconditioner look like this one. So, A gamma is a velocity block, and B transpose is the pressure block, and S tilde is what is known as the Schur complement. Okay. And the inverse of this block matrix is defined here in P inverse equation. Okay. Where the inverse of the Schur complement is minus nu. Nu contains all the viscosity terms times MP inverse. I'm going to tell you what is MP inverse means. And then gamma coming from the newly added augmented Lagrangian term times W inverse. Okay. So where MP is the pressure mass matrix. Okay. Why we use pressure mass matrix? Because it's easy to compute. Okay. One can also come up with a different choice of this MP and then test the stability. So that is still an open problem for the convection dominated flow models. Okay. And then even this itself, the choice of this, even a simpler mass matrix entry is itself have its own challenges. Okay, so the S tilde inverse is by this choice simply B A inverse B transpose inverse plus gamma times W inverse, where there is also a scope for doing a different W. This could be a very good PhD thesis. So one can take different choice of W and study the stability of this numerical method. Okay, so here also in our as a first step, we just use this for the choice of W. We just use same as MP, means we just use that mass matrix coming from pressure block. Okay, why pressure block? Because these entries you have already computed it, so you don't have to assemble them separately or newly. Okay, so this sure complement luckily uh, is going to do a trick for the convergence. So now that we have assembled our block matrix A tilde, and we have come up with a preconditioner P, and then the inverse of P can be done by any linear solver. Either you can use conjugate gradient, or you can use generalized minimal residual method, GMRES method. Okay, so we now have A tilde and P inverse, and we will go back and look at this linear problem or matrix problem, and we solve for y, and then once we know y, we construct x. Okay, so and then once you do this, you have to test your method against some known results. So the theorem says that because we are approximating the velocity variable by a quadratic polynomials, so in the convergence in the L2 sense has to be equal to 8, and convergence in the H1 sense has to be equal to 4. When you reduce your mesh size smaller and smaller, or you introduce lot of cells, so this is what you have to achieve. In the L2 sense it is 8, in the H1 sense it is 4. Luckily we have achieved that, and then we also look at the convergence rate for pressure. Since pressure does not have any derivatives, because it lost the derivative by the integration by parts, so you just have to achieve 4 rate of 4, like H1 error for the velocity, because we are approximating pressure by linear polynomials. Okay, so yes, we have achieved that. So that means we can trust our code and we can trust our method. And we also test our method by results in the literature. The one famous problem done by Gia, I think this is 2000 paper. So he has results from finite difference method for different Reynolds number, and we also did the same thing. We compared our horizontal and vertical velocity components on horizontal and vertical line with the results of Gia, and we matches very closely. Okay, so that means we have some trust on our results. And once you have all this, you can take a problem that is done explicitly in the literature. The problem that is done explicitly is the moving boundary problem. What is this? Moving boundary problem describe the situation where you have two horizontal plates. The upper plate is moving, but the lower plate is not. That is one situation. Or you can move the upper plate and lower plate in the opposite directions, or you can move both upper and lower plate in the same direction, either towards right or left in the same direction. Okay, so we did all the three, and what I'm showing you here is the comparison of the results obtained for our the model that is done in this talk, and also comparing with the standard model. So the last pictures to your right is the results of the velocity contours obtained for Darcy-Brinkman Forchheimer model. And if you go towards left, the second picture is the Darcy-Brinkman. The first picture is just the Brinkman model. Okay, and you see that the center largest vertex is doing something. It is moving towards the right, and this problem is done for the exact same boundary condition in all three situations. Okay, so this is also interesting to pick up why I mean, why it is happening, what is happening, and also how do you control these eddies. And in the case of Darcy Brinkman Forchheimer, you see that more than one eddy is developed, but compared to the case of just a Brinkman model. And then also the largest value in the contour also could be interesting, and could be interesting to compare with the existing results. Okay, so all those are done in the paper, but it is still under review. But thank you very much for your listening. I think you can, if you have questions, you can let me know.
Thank you, sir. Thank you for your presentations. Now it's the time to ask the queries. I kindly request the participant to ask the queries or post the queries in the chat box. I request the participant to ask the queries.
Look like there are no questions. That means I did not do a good job.
No, sir. You explain it clean and clear, sir. So
Thank you.
only
Thank
there is a no queries.
you. Thank
The chat box is filled with only a positive comments, sir.
you. Thank you. Thank you. Yeah, I see that.
Let's formally end up the session. The vote of thanks. I would like to call Ms. S. Felicia, Assistant Professor, Department of Mathematics, to deliver the vote of thanks.
Good evening to one and all gathered here. On this wonderful evening, I would like to present the vote of thanks. I take this golden opportunity to thank our eminent resource person, Dr. S.N. Mallikarjuna, Professor of Mathematics, Statistics. My immense knowledge under the topic of fluidics mechanics. It was a wonderful and very useful presentation, sir. Thank you. Today's FDB gave a deep insight into the topic and revealed some interesting facts. Also, I would like to thank Dr. Kavita, Vice Chancellor, DMI, St. Eugene University, Zambia, Administrator, Reverend Sister A. Malatoti, Dr. R. Ruben, Principal, St. Joseph's College of Arts and Science, Chennai, for their continuous support and guidance for conducting this international FDP. Also, I would like to thank Mrs. K. Sujata, Head Department of Mathematics, Coordinator, Mrs. S. Rajeshwari, and Dr. V. Govindan, Research Coordinator, Zambia. Faculty and fraternities and all the participants for attending this session. Last but not least, I would like to thank our technical team and Department of Visual Communication for their continuous support in conducting this program. Once again, thank you all.
Thank you, ma'am.
Professor, thank you very much, Professor.
Thank you, Dr. Govindan, for the
Yeah, yeah, very
opportunity and
nice.
nice
Thank you.
and nice meeting you all. Bye
Thank
bye.
you,
Take
sir.
care.
Thank you. Now it's a photo session, so I kindly request the participant to switch on the camera. Thank you all. And special thanks to all the participants. We will meet by tomorrow's sessions. I request the participant to fill the feedback from attendance which is posted in the chat box.